5.6 Centers of mass. Let's draw out a region R in the plane, and then let's let that be the space occupied by a lamina. We can compute the area of that lamina by looking at a double integral with integrand 1. If we assume that this lamina has a density function, rho of xy, so at every point, this function produces back a scalar telling us how much mass is present at that single point. Add up all of those values to recover the total mass of the lamina. Now, what is a center of mass? A center of mass is going to be the point in the lamina such that if we placed a fulcrum underneath the lamina at that point, that the two-dimensional flat lamina would balance perfectly on the tip of that fulcrum. To compute the center of mass, we need some nice tools, which are called moments. In particular, we need the first moments. The first moments are going to be the first moment about the x-axis. The first moment about the x-axis, m sub x. If we envision the x-axis, and then we want to move away from the x-axis, we are going to change y values. If we want to move away from the x-axis, we change y values. So we look at the y value at any point in our region and then weight it by the density function, add up all of those quantities, and then name that value the first moment about the x-axis. If we swap the roles of x and y, we'll come up with what's called the first moment about the y-axis. If we have a y-axis, we can be either to the left or to the right, and the amount that we are either left or right of the y-axis is captured by the x-coordinate of a point. So when we add up all of those x-coordinates which have been properly weighted by the density function, we arrive at a value, and we term that value the first moment about the y-axis. So these quantities are capturing how much is above and below, how much is left and right of the coordinate axes. So that when you take those quantities and you divide them by the total mass that is present, you come up with an average. You want to know how far left or right you should be in the plane. That means that you want to reference against the y-axis. How far left or right you reference against the y-axis. If you want to know what the average y-coordinate is, then you need to reference against the x-axis. So this numerator is the first moment with respect to x. This is the center of mass, denoted x bar, y bar. It is a point in the lamina, such that a fulcrum placed there, the lamina would perfectly balance. Excellent. Here's a nice example from the book. We have given to us a picture which is described as that underneath y equals x squared and above the x-axis between x's from 0 to 2. Let that region be denoted R, and let that lamina have a density function rho, which is given by x plus y. We want to find the mass, the moments, and the center of mass. To go about that, finding the mass is simply looking at the double integral, where we take the density function as integrand. The density function is x plus y, and we have ways to describe the region to come up with our bounds of integration. Having found the mass, we can then go about finding the first moments. The computation is very similar. We're going to have this double integral with integrand rho. And then to find the first moment with respect to x, we add in to the integrand a factor of y. First moment with respect to y, we add in a factor of x. Having computed these quantities, we can then compute the center of mass by simply taking quotients. Beautiful.